In this lecture, let us learn the spectrum and bandwidth of wideband angle modulation. If you recall, the frequency modulated signal is written as follows. X of t is equal to sigma n is equal to minus infinity to plus infinity j n of beta. It is the Bessel function of order n with the parameter beta times cos of omega c plus n omega m times t. Right? Recall this equation for frequency modulation, frequency modulated signal. Right? Now, if we expand this equation, let us say substitute n equals 0, then you will get j0 of beta times cos of omega ct. Substitute n equals plus or minus 1, you will get j1 of beta times cos omega ct, comma cos omega ct plus omega mt, and substitute n equals minus 1, j minus 1 of beta cos of omega c minus n omega m times t. Similarly, substitute n equals plus or minus 2, then you will get j2 of beta cos of omega c plus 2 omega m times t, comma j minus 2 of beta cos of omega plus omega c plus not plus minus 2 omega m times t. Substitute n equals plus or minus 3, then j3 of beta cos of omega c plus 3 omega m times t, comma j minus 3 cos of omega c minus 3 omega m times t, and so on so forth. Right? It keep on goes up to n equals plus or minus infinity. Right? Now, if you try to plot in the frequency axis, let us say this is my frequency and somewhere this is 0 and this is fc. Okay. Now, you have the magnitude of j, let us say j0 of beta. Then you have j1 of beta times cos omega c plus omega m, j minus 1 of beta omega c minus omega m. This is not n, okay, because we substituted 1, right? Omega c minus omega m. So, I have two components. Okay, one is omega c plus omega m. Let me now use a frequency axis instead of fc omega c. Let me use fc here. Then you will have omega c. Let me denote. This is fc plus fsum. Fm. Let us say the coefficient is j1 of beta, and this point is fc minus fm. The coefficient is j suffix minus 1 of beta. Why they are opposite each other? Because they are odd function at odd values. Okay, please recall the properties of your Bessel functions. j1 of beta is equal to minus of j minus 1 of beta. That is why it is coming like this. Now, when this point is fc plus 2fm, you have this point is j2 of beta, and here also j2 of beta. This point is fc minus 2fm. Right? Then this one is j minus 3 of beta, and this point is going to be what? fc minus 3fm. Similarly, in the right hand side, this will be plus 3 of beta, and this point is going to be fc plus, let us say 3fm, and so on so forth. Like that, it keep on grows up to infinity, and this side also it keep on goes up to minus infinity. Now if you want to find the total bandwidth, what is the bandwidth? The bandwidth will go to infinity. Theoretically speaking, the bandwidth is infinity. Okay. Now what I am going to do is, instead of plotting in the normal frequency axis, let me normalize the frequency axis. Okay, let me draw again the frequency axis like this. Now my axis is not f, here it is f. Okay, this one is f here, but here I am going to subtract the carrier frequency from the f minus fc divided by fm. That means I am normalizing the frequency axis. Okay, I have chosen the frequency axis to be normalized to 1. I have looked at the frequency deviation from the center frequency fc, normalized with respect to the modulating signal frequency fm. Okay, therefore if you substitute in this point, okay, here f equal to fc in this point, right? So if you substitute, what will happen? F minus fc by fm, normalization. Now if you substitute f equal to fc, then what happens? Fc minus fc divided by fm. This is 0. Therefore this point corresponds to 0. Okay, so this point corresponds to 0. And this point, what is this point? fc plus fm. This one is fc plus fm. Substitute in the formula. So f minus fc by fm, in this if you substitute fc plus fm minus fc divided by fm, fc get cancelled, fm by fm, it is equal to 1. Therefore this point is normalized to 1. Similarly this point is normalized to 2 and this point is normalized to 3. What about this point? Fc minus fm, substitute there in this formula. So fc minus fm minus fc divided by fm, fc get cancelled, fm cancelled, so minus 1. So this point becomes minus 1. What about this point? In this point this is fc minus 2 fm, so this becomes minus 2, this becomes minus 3. So I am normalizing the frequency axis, right? So this is 0, 1, 2, 3, minus 1, minus 2, then minus 3, and so on so forth. Okay, this is 0. At 0 my coefficient is, let's say, J0 of beta. Okay, at 1 the coefficient is J1 of beta. At minus 1 it is just opposite of that, J minus 1 of beta. At 2 it is J2 of beta, and this one is J minus 2 of beta. Then this is going down, J minus 3 of beta, and this one is positive, J3 of beta, and so on so forth. It keep on goes. Okay, J4, J5, J6, and so on. The left hand side also you will get maybe let me complete for a few more terms. J4 becomes, this is J4 of beta, and here also J4 of beta, and this one is J minus 5 of beta, and then let's say this point is J5 of beta, and it keep on goes, and say this is J6 of beta, and this also J6 of beta, minus 6 of beta, and so on. And here the frequency axis is normalized, fc minus fm, sorry, f minus fc divided by fm. Okay, that means, oh my god, squirrels are making so much noise. When I say this point is being 0, that means f equals of fc here. Okay, and at this point f equals fc plus fm. Okay, so we are locating at the spectral component at the point where the deviation is fc plus fm, and this point is fc minus fm. So basically this component denotes, this one denotes fc plus fm, and this one denotes fc minus fm. So instead of fc plus fm, fc minus fm, I have written 0, 1, minus 1, 2, minus 2, and so on and so forth. But remember that the point denotes the frequency fc. Okay, this point, 0 point denotes the fc because it is normalized. Okay, therefore this point denotes the component at carrier frequency, and this point denotes the component at fc plus fm, and this guy denotes the component at fc minus 2 fm, and this denotes fc minus 3 fm, and so on so forth. Okay, so the components are fc minus fm, fc minus 2 fm, fc plus fm, fc plus 3 fm, like that it goes. And as you can see, j1 of beta and j minus 1 of beta have opposite signs. Where is j minus 1 of beta? It is here, and j1 of beta, it is here. Both are in opposite signs, but j minus 2 of beta and j2 of beta have the same sign. Why? Because of your Bessel functions property. Similarly, for j3 of beta, again they are opposite signs, positive and negative. Okay, j minus 3 of beta has opposite sign of j3 of beta, and so on so forth. So I see a very large number of spectral components are there in this. So it is a wideband signal. Why is it called wideband? The bandwidth is very large because you have a large number of components, large number of spectral components. So in general, when beta is not small, if beta is not small, we call it a wideband angle modulated signal. Okay. So nearby my room there is a tree, and the neem tree, in that some 2-3 squirrels are there. Just keep on making noise. Okay. What to do? So although your modulating signal contains a single frequency component, what is your modulating signal? M of t is equal to am times cos of omega mt. How many frequency components are there? Only one frequency component. Okay, in the cos omega m contains only one frequency component. What is the frequency? Fm, that's all, no more frequencies. Okay, so even though your modulating signal contains only a single frequency component Fm, your modulated signal contains very large bandwidth. It doesn't matter whether your modulating signal has single frequency or multiple frequency. When you do the frequency modulation, the modulated signal contains a large bandwidth. Okay, so I think this is very reasonably clear about the Bessel functions and it's some of the important properties. Okay, now you appreciate what that typical spectral plot of angle modulation is. It looks like this. Okay, if you take AM modulation, you have only 3 line spectra. If you take AM, it contains only, let's say this is 0, carrier frequency, Fc plus Fm and Fc minus Fm, that's all, only 3 lines in the case of AM. But in frequency modulation, you have a large number of lines corresponding to just the presence of single frequency message signal at the input. Even though the input signal contains a single component, single frequency component, but your modulated signal contains a very large number of lines corresponding to the modulated signal. So that is an important point to note down. Okay, now let us look at the spectral properties. In the previous class we looked at properties of the Bessel function. Now let us look at spectral properties of FM signal, wideband FM signal or FM signal, not an issue. Okay, now let us summarize what are the important spectral properties that we can derive. The spectral properties which are implied by the properties of Bessel functions. Okay, so the first point is we see that if you look at the spectrum, that it contains a carrier component. Where is the carrier? This is the carrier. Let me delete all these guys so that I can explain you very well. So, so the first point is we see that the spectrum contains a carrier. Where is the carrier? This is the carrier component, carrier plus an infinite number of sidebands, J1 of beta, J2 of beta, J3 of beta, J4 of beta, J5 of beta, all are located at Fc plus Fm, Fc minus, Fc plus 2 Fm, Fc plus 3 Fm, Fc plus 4 Fm and so on and so forth in the positive side. Then in the negative side, Fc minus Fm, Fc minus 2 Fm, Fc minus 3 Fm, Fc minus 4 Fm, like that it keep on goes. Okay, not just two side bands like we had earlier for AM signal. Okay, so both on the positive side as well as on the negative side we have large number of frequency component, infinite number of side bands. I mean frequency components like Fc plus or minus n times Fm. Unlike the case of AM, we had only Fc plus or minus only Fm, that's all. Okay, so the first property of your first spectral property of your FM signal is like the modulated signal has carrier plus infinite number of sidebands. Okay, so Fc plus or minus NFM. I am sorry, I am helpless. This squirrel is keep on making noise. Okay, this is the first property. Second, relative amplitude and number of significant spectral components are not that much important. That is relative. Okay, so the magnitude of the Bessel function or Bessel coefficient depends on the value of beta. Okay, like we saw for a small modulation index, carrier has the largest component. Recall from the properties of your Bessel function. Other components are much smaller. Okay, so as beta increases, there can be some values of beta where the carrier component is 0. And all energies are contained in the sidebands. Recall this property from your Bessel function. I already discussed this. So therefore, relative amplitude and number of significant, even though it has infinite number of sidebands, only a certain number of sidebands has significant spectral components. Significant spectral components depends on beta. If you recall from your Bessel functions, like if beta is much less than 1, then your J0 of beta is approximately equal to 1 and J1 of beta is equal to approximately equal to beta by 2 and J2 of beta is approximately equal to 0. So this J2 of beta, J3 of beta all are goes to 0. So therefore the coefficient depends on the value of the beta. Right. Now if in this spectrum, even though it has large number of spectral components, but if you look at this J3, J4, J3, J4, J5, they have insignificant amount of energy or insignificant amount of power. So in such case, no need to consider those components. So your life becomes very simple. Okay, therefore this coefficient, the amount of energy or amount of power it contains, depends only on the value of beta, where beta is the modulation index. So that is a second property. And the third property is, we have seen that for beta much less than 1, as I said, only the first three are significant: j0 of beta, j1 and j minus 1 of beta. Okay, so in this case what happens, your spectrum is similar to that of AM signal. Okay, while it is similar, it is also slightly different. Okay, it is not exactly similar to AM, but it is slightly different from AM, but its spectrum is almost finite. Okay, so if beta is less than 1, as I said, this j2 of beta is equal to 0, j minus 2 of beta is equal to 0. In that case, your xfm of t has only three components: j0 of beta times cos omega ct plus j1 of beta times cos of omega c plus omega m times t plus j minus 1 of beta cos of omega c minus omega m times t. That's it. Only three components. Rest of the components will become 0. So the spectrum is similar to that of AM, except for phase reversal. This one is just inverse of your j1 of beta. Therefore this I can write as, I put minus here. I remove this plus and I put a minus here. Okay, so that is the only difference compared to AM. So there is minus here for FM. For AM you have plus sign. That's it. So the narrowband FM, this is a case for narrowband FM. Why is it narrowband FM? Because your bandwidth is very less than 1. Beta is much less than 1. That is why this is my narrowband FM signal. So the narrowband FM, which is the FM defined to rise when beta is very small, and in that case the spectrum is similar to that of the AM signal. In the sense, it has only two side bands, FC plus FM C, FC plus FM and FC minus FM. That's it. So the third point is, let me write down, for beta is much less than 1, then only, as I said, j0, j minus 1, j plus 1 are significant, remaining are insignificant. Okay, so in this case spectrum is similar to that of AM, except for the phase reversal. For whom the phase is reversed? Of the lower sideband component. Which is lower sideband component in this expression? This is the lower sideband component, LSB. Omega c plus omega m is the upper sideband component. In the lower sideband there is a phase reversal. Okay, minus sign, 180 degree phase reversal. That is the only difference between AM and narrowband FM. Okay, so therefore we can compare narrowband FM and AM signal, AM with carrier. That is the only difference, 180 degree phase reversal. And the fourth property is, as against with property number 3, when beta is much greater than 1, or let me say beta is greater than 1, large, very large, the number of spectral components are very large. You can see from the figure, because in that case this j2 of beta, j2, j minus 2, j3, j minus 3 are significant components. It has significant amount of energy. In that case you cannot neglect, you cannot disregard that. Therefore when beta is large, then number of spectral components are very large, and such a signal is said to be wideband signal, or wideband FM, or wideband PM. Okay, this implies large bandwidth. Okay, these descriptions of bandwidth are qualitative. Okay, So small or large is qualitative, it's not quantitative. So a natural question arises, can we convert this into a quantitative value? Okay. So for beta is greater than 1, I mean much greater than 1, I put one more greater than, number of significant spectral components is large. So in such a case, this is called a wideband FM, and bandwidth is large. That's it. Now we need to we need to specify, okay, how big it is. We cannot simply say large or small. That all are like relative terms. So qualitatively and quantitatively we can say. Can you say this? Okay, this is the bandwidth. Okay, this much is the bandwidth. Like that, how will you say that? Okay, now let us address that issue. And like this is a slightly tricky question. Okay, tricky situation here, because you cannot say, okay, this is a, how do you find, because you have infinite number of components. In such a case, it is something difficult to say the exact bandwidth in the closed form. Okay, theoretically, no matter what the value of beta may be, whether it is small or large, the bandwidth will be infinity. Okay, so whether you take beta is small or beta is big value, then theoretically speaking the bandwidth is infinity. Okay. So based on this fact, we need to define the bandwidth in a particular way, and then come up with a quantitative figure for the bandwidth. How do you do that? Let us see. The next one is quantitatively, let us define the bandwidth by using some approximation, that's all. Bandwidth of angle modulated signal. When I say angle modulation, it includes both FM and PM. No need to do the analysis separately for PM from AM. Okay, fine. So let's do some discussion on that, on bandwidth. So we would like to look at the bandwidth of angle modulated signals more quantitatively, rather than simply calling it a large bandwidth and a large bandwidth or small bandwidth. So as I said, strictly speaking, the bandwidth is infinity. But infinity is not a finite number, right? You cannot simply come and say, okay, this is my frequency modulation and my bandwidth is infinity. You cannot say like that. But I just mentioned that in practice we make use of this fact that from your Bessel's function, if you recall, limit n goes to infinity. That means when n becomes large number, then your Jn of beta becomes insignificant. It tends to 0. And this is again very helpful to define the bandwidth quantitatively. Okay, and this property is again coming from the this result is again coming from the properties of the Bessel function. Okay, I think this property I did not mention in the previous lecture. So this is the property of Bessel functions. I think I didn't mention this in the last lecture. Limit n goes to infinity, then Jn of beta becomes 0 or tends to 0. Therefore, the Bessel function of infinite order identically is 0. Okay. Bessel function of infinite order, because n is order of the Bessel function. So this is the property of your Bessel function. So now how do we define the bandwidth? To define the bandwidth, let me first define a ratio, something called power ratio. Okay, so which we call the power ratio Using this technique, let us define the bandwidth. Power ratio, let me denote this power ratio by P suffix R, and it is defined in the following manner. Suppose I consider K sidebands on either side of Fc. That means what? Okay, let's say this is my Fc plus Fm, Fc plus 2Fm, Fc minus Fm, Fc minus 2Fm. Like this, let me define up to Fc plus Kfm. Right? So, what is the bandwidth? This distance is Fm, and this distance is again Fm, and this one is again Fm. How many Fms are there like this? K times of Fm. Or you can simply find the bandwidth from here to here. What is the bandwidth? Bandwidth is equal to upper frequency Fc plus K times F suffix m minus Fc. So, this Fc and that Fc will get cancelled, therefore, you will get K times Fm. What about in this side, lower sideband? This is for upper sideband. For lower sideband, again you keep on go towards like this. Let us say this is Fc minus K Fm. Now, what is the bandwidth from the lower sideband? Again, this is upper frequencies Fc minus Kfm. I am sorry. The upper frequencies Fc minus lower frequencies Fc minus Kfm. So, Fc will get cancelled. So, again Kfm. From the lower sideband, the bandwidth Kfm. From the upper sideband also Kfm. Therefore, the total bandwidth is equal to 2 times K times Fm if you consider K number of sidebands on the positive side and K number of sidebands in the left hand side. Right? Therefore, now let us calculate the energy in this K number of sidebands. Look at the energy in this part, okay, of the signal. This is the approximation. Okay, we are approximating the actual signal. Now let us take the ratio of this energy from this number of sidebands. Okay, I am calling either energy ratio or the power ratio. Actually, power ratio is more appropriate. Let us call it power ratio. Okay, we will not talk in terms of energy ratio. Now, what will be the power contained in this? In this components? How many components are by the way? You have Fc one component, second component, third component, up to K number of components. If you add up Fc also, how many components are there? K plus 1 components. And from, because including Fc, first term, second term, third term, up to kth term, right? So, therefore, K plus 1 terms in this side. Let us say K equal to 4, then what will happen? First Fc is the first term, Fc, second term is Fc plus Fm, and the third term is Fc plus 2Fm, fourth term is Fc plus 3Fm, and fifth term is Fc plus 4Fm. When K equals 4, then you have 5 components in this side. From this side you have 4 components. Therefore, 5 plus 4, 9 components. That is, when K equals 4, then you have 2K plus 1 components in the spectrum. So, power in this K number of components in the upper sideband and K number of components in the lower sideband, and 1 component at the carrier frequency. In this case, your power is equal to, you put the summation, n is equal to minus K2 plus K. You stop between this limit. Then Jn of beta squared whole divided by 2. Recall this definition. Let me write down one more expression, then I will come back to this. What is your power? Suppose if you have A times cos of omega ct, what is the power of this guy? A square by 2, right? Now, what is your modulated signal? x of t is equal to sigma n is equal to minus infinity to plus infinity jn of beta jn of beta a times ac times cos of omega ct. What is the power component in this? How do you find out? Simply this already we did it, okay, in the last class. N is equal to minus infinity plus infinity jn squared of beta times ac squared over 2, and ac square is constant, 2 is constant. You can pull out from the summation ac square by 2 sigma n is equal to minus infinity plus infinity jn squared of beta. Now in this you are going to consider only k components in the upper sideband and k components in upper sideband and k components in the lower sideband, and one component at one spectral component at the carrier frequency fc. So totally I have 2k plus 1 components. Therefore this summation becomes like this: n is equal to minus k2 plus k, then ac squared, you can see. So power in k sidebands. Maybe I'll write them properly. I mean k upper sidebands, k lower sidebands. Okay, so are power contained in 2k plus 1 terms. That is more appropriate. Power contained in 2k plus 1 spectral components or spectral components. This is sigma n is equal to minus k2 plus k, then ac squared by 2 jn of beta. Now this ac squared is constant by 2 summation of n is equal to minus k2 plus k jn squared of beta. Okay, now let us take the ratio, power ratio. Power contained in the 2k plus 1 terms divided by total power. So power ratio, as I said, is denoted by PR is equal to power contained 2k plus 1 terms, which is ac square by 2 sigma n is equal to minus k2 plus k jnr square of beta divided by total power. Total power is n is equal to minus infinity plus infinity jn square of beta multiplied by ac square by 2. These two guys will get cancelled. What is this value? As I said, this value is equal to 1, right? Therefore the power ratio is sigma n is equal to minus k2 plus k j naught squared of beta. Why is it equal to 1? This we already proved in the previous class. Go through that. Okay, therefore this I can write as j naught squared of beta plus 2 times, because you are squaring, no, therefore 2 times sigma n is equal to 1 to k j n of beta. This is my power ratio. Okay, now the way we defined the bandwidth is as follows. We say that for a signal to have bandwidth, whatever we define the bandwidth to be, it should be most of its energy in that band. If it has no insignificant amount of energy in that sideband, we no need to consider that. Simply we can disregard. Okay, only thing we need to know is what is the definition of the most. How much energy we are going to consider. Either you are going to consider 90% of the total energy, or 90% of the total power, or 80% of the total power, or 95% of the total power. It is up to you. Okay, so it depends on the modulation index and depends on the requirement of the system. Okay, now we can take some arbitrary figure, and generally accepted figure is like 98%. So what are the spectral components which contains 98% of the total power, then that will be considered as the total bandwidth. Beyond the 2% of power is distributed among many more components, that we can disregard. So the way we define 98% bandwidth of any signal is, otherwise they have infinite bandwidth, that those band of frequencies over which the signal contains 98% of its power. That means the value of the power ratio is 98%. Okay, so this must be equal to 98%. If you want 100%, then you should be ready to give infinite amount of bandwidth. So basically what we need to figure out is for what value of k, this is k, right? So for what value of k this ratio turns out to be 98. Either when I substitute k is equal to 5 or 6 or 7 or 8, whatever it is you substitute there, and find out that whether it gives 98% of the total power. Okay, so that is the next thing that we need to consider. And now for a given application, the bandwidth is defined for a specific value of power ratio. It is not like uniform definition. It depends on the beta value, and for whatever value that you select, the bandwidth will then become, what is the bandwidth now? Can you tell me from the figure? If you consider k number of side bands, what is the bandwidth? Just now we calculated. Okay, so it is 2k times fm. Okay, if you consider k number of side bands, the bandwidth is equal to 2 times k times f suffix m, where k is the number of spectral components. Above Fc. Okay, you recall the figure. Just now we calculated. Okay, if you calculate total, like you have, this is Fc plus Fm, and keep on goes Fc plus Kfm. What is the bandwidth? This bandwidth is k times Fm. In the lower side band also we have k times Fm. So total bandwidth is 2 times k times Fm, Kfm plus Kfm, 2 Kfm. So whatever the value of k would give rise to the would give you that value of PR. So this implies that the bandwidth is 2 Kfm. So for the power ratio to be greater than or equal to 0.98, that is 0.98% bandwidth. Now what will you do? If you look at the table of the Bessel functions, okay, this we cannot simplify here. You cannot simplify, or you cannot simply find out what k value will give you the 98%. But the Bessel functions are well studied by mathematicians, and it is tabulated in the textbook. Okay, so we need to look at the table of Bessel function. At what value of k this becomes 0.98. That you look at the table of the Bessel function. A very interesting fact comes to light, that if you choose PR to be greater than 0.98, the value of k that you need okay, is determined by the quantification value, how much you want to say, 0.98 or 0.95 or 95% or 90%, like that. Okay, therefore this ratio PR becomes 0.98 and depends on the value of beta. So the interesting fact is this PR depends on power ratio, depends on the beta and k. but there is a very nice closed form. Of course, it is not closed form in mathematical sense, but it is empirical. In the empirical sense, empirically it is found that for a given value of beta, if you choose k to be beta plus 1, just one more than the value of modulation index. Okay, this all comes from your Bessel's function table, right? Suppose if you take beta is equal to 5, then if you choose k is equal to beta plus 1, that is 6. When k is equal to 6, then your PR contains 98% of the power. In case if you choose beta is equal to 10, then your PR contains 98% of the power when k is equal to 11. That means what? When beta is equal to 10, then you need to consider only 10 components in the upper side band and 10 components in the lower side band. No need to consider infinite number of side bands. That's what we mean by when beta is equal to 10. That means what? This is my FC. You consider FC plus EFM, FC plus 2FM, dot, consider up to FC plus 11 FM. That's all. No need to consider anything else beyond that. Similarly, you consider FC minus 11 FM. So this band contains 98% of the total power. Similarly, when this is for beta is equal to 10, modulation index is 10. In case if you choose beta is equal to 5, then you consider only 6 component, FC, FC plus FM up to FC plus 6 times FM, and in this side also FC minus FM up to FC minus 6 times FM. So you consider this terms enough, that is enough. So this spectral component, this 11 spectral components, how many? 11 or 13? 13 components, 2k FM, right? So 13 spectral components, 1, 2, 3, 4 up to 6 components in this side. This side 1, 2, 3, 4, 5, 6 components, and the carrier is 1 terms. Therefore 13 spectral components. This 13 spectral components contains 98% of total power. So this result we got from the table of your Bessel function. Okay, look at the Bessel function table. You got very interesting result. Okay, you just take one value more than the modulation index, that is enough, and that value of k would lead to 98% or larger. So this is something that you look at empirically from the table of Bessel functions. Empirical result. Okay, this is obtained from table of Bessel functions. So no need to study in detail about this. Okay, just we take this result as it granted and then let us move on. Okay, so I cannot prove it mathematically here. In fact, not needed. Okay, maybe it can be proved, but I think we will take it as it is. So for PR greater than 0.98, it is noted that k can be taken as integer part of b plus 1, because after all k is an integer, right? If you look at the summation, what is k? K is an integer. In case if it comes some fraction value, then make it as the integer part of that ceiling function. Okay, so let me write down this point. For the power ratio PR greater than or equal to 0.98, it is noted that k is equal to integer part of beta plus 1. That means k is equal to rounded off. Okay, integer, that's it, integer part of b plus 1. If you take 6.01, then you take it as 7, that's it. So this is the empirical result. I think no need to explain about the meaning of empirical. Okay, so this is an empirical result. It is obtained by just looking at the nature of the Bessel functions, and therefore that tells us quantitatively the value of the 98% bandwidth. In case no, I want 99%, then you can look at the Bessel functions table, and then based on that you pass the as many number of sidebands as it has. So this implies that the bandwidth is what is the bandwidth now? Bandwidth is twice 2 times of beta plus 1 times Fm. That's it. So therefore bandwidth is equal to if you multiply 2 inside, because what is your beta? Beta is equal to delta F by Fm. So recall this definition from the previous lecture. Fm plus 1 into Fm. So 2 times delta F plus Fm. So this is my bandwidth, and this is the expression for bandwidth of an FM signal approximately. Okay, this is not exact, it is approximately. So as you can see, there is a very simple closed form result. Okay, and this result is well, only for the special case. What is the special case? Your modulating signal m of t is am times cosine omega mt. It is not suited for a general arbitrary signal. Now recall this definition. I am going to rewrite the definition. Bandwidth is equal to 2 times of beta times Fm plus 1. Now let us interpret this beta times Fm. What is this beta times Fm? If you look at the expression for Fm or PM signal, okay, that you have here, what is your Fm signal? X Fm of t for modulating signal is AC times cosine of omega ct plus beta times sine omega mt. This is what we derived. Recall this function. Okay, this is the expression for Fm signal. Now let us give some physical meaning for this beta Fm. What is the physical meaning? So how do you give the physical meaning for this? What we mean by beta Fm? How will it arise? To address this issue, to answer this question, let us take the argument. What is the argument? Omega ct plus beta times sine omega mt. If I differentiate the argument, what will happen with respect to time? Omega ct becomes omega c, and this becomes beta times omega m times cosine of omega mt. This is what I get after differentiating d by dt, right? Now what do you understand from this? The instantaneous frequency, this is my total phase angle, instantaneous phase angle, right? Recall from the previous lecture, instantaneous phase angle. Instantaneous phase angle. And what about this? Instantaneous frequency. So your Fi of t, this is denoted by theta I of t, and this one is Fi of t. Your Fi of t is equal to 1 by 2 pi times d theta I of t. That's what you got here, divided by dt. Therefore omega ct I can write as 2 pi fc divided by this 1 by 2 pi multiply, okay. Like this. 1 second, I'm confusing. Let me rewrite properly. This is not the way to teach. It will create lot of confusion. Now this is instantaneous phase, as I said. How do we denote the instantaneous phase? How did we denote? Theta I of t. Theta I of t is equal to omega c of t plus beta times sine omega mt. Now differentiate. D theta I of t divided by dt is equal to omega c. It's not function, omega ct plus beta times omega m times sine becomes cosine omega mt. Again it is a function of frequency. Look at here. Sorry, function of time. Here it is a time parameter, so it is theta I of t. So that is why we write, instead of writing theta, we are writing theta I of t. Now the instantaneous frequency. Instantaneous frequency. How do you denote the instantaneous frequency? Recall, it is fi of t. What is fi of t? Fi of t is 1 by 2 pi by definition. Recall from your school physics. Okay. So d theta I of t divided by dt. So 1 by 2 pi and d theta I of t dt is omega c plus beta times omega m cos omega mt. Now rearrange this. 2 pi fct, 2 pi fc divided by 2 pi plus beta times 2 pi fm divided by 2 pi cos of omega mt. 2 pi will get cancelled. So fc plus beta times fm times cosine omega mt. Now can we give the physical meaning for this? What is the maximum value? This is my fi of t. Fi of t maximum. Fi of t maximum is equal to fc plus, at the most this guy can be 1, your cos function, right? Therefore beta times fm. What is your fi of t minimum? At the most this guy is equal to minimum value minus, not at the most, at least minus 1. Okay. Therefore fc minus beta fm. So the maximum instantaneous frequency is fc plus beta fm, and the minimum instantaneous frequency will be fc minus fm. So how much it is deviating from the carrier frequency? See, this is my carrier frequency fc, and it goes up to all the way fc plus beta fm, and it goes up to, in the negative side, up to fc minus beta fm, right? So how much it deviates from the carrier frequency, that is called a frequency deviation. Okay. So maximum value that the signal will have of frequency deviation. Because the frequency deviates, deviation becomes this guy beta fm maximum, either plus beta fm or minus beta fm, because your cos omega mt at the most will be 1 and at least minus 1. Therefore the maximum value of the frequency deviation would be beta times fm. This beta times fm is called a maximum. It cannot deviate beyond that. That means it cannot go greater than fc plus fm. Maximum frequency deviation. Therefore beta fm is nothing but maximum or the peak value of the frequency deviation. You can say maximum or peak value of the frequency deviation. Okay. So that is the signal exhibit, your modulated signal will exhibit. So the instantaneous frequency of both the PM signal and the FM signal keep on varying. It is not fixed. Okay, you look at the definition, you look at the waveform. When I say this is my modulating signal, your FM signal will be, it keep on changing, the frequencies keep on changing. Some point it is very close by, and sometimes it is very sparsely spaced, and then again it is very closely spaced, like that. At different times you have different instantaneous frequency. Remember this, remember that from these plots that we made for the FM signal. At some point along the time axis, the signal was highly compressed. Highly compressed. That means what? More number of cycles. So maybe it reaches FC plus delta FM. At some point, if there is no carrier, then it will be FC. And at some point, it will be sparsely spaced. FC minus delta FM. Okay, when the instantaneous frequency was large, this is the maximum amplitude, it is highly compressed. At some other points, the signal was much more sparse. Look at here, much more sparse. And there the instantaneous frequency was smaller than your carrier frequency FC. Therefore, the peak value of the instantaneous frequency deviation is equal to beta times FM. Not this FC plus FM, I am sorry, I wrote wrongly. Beta times FM. So please remember that. Therefore, you can also write this formula like 2 times beta plus 1 times FM as 2 times delta F plus FM, and this we just now we derived. Okay, this delta F is called a peak frequency deviation. Now the analysis that we have just carried out is valid only for, this is valid only for what? Only for whom? Only for sinusoidal modulating signal. Modulating signal, not modulated signal, okay? Modulating signal means message signal, that's what. Either you can call message signal or modulating signal. But in practice, we are anyway not going to use sinusoidal signal as a modulating signal, right? We generally use a speech signal, music signal, voice signal. For more general signals, it is approximately possible to argue out the bandwidth of FM signal. Okay, so we can argue it in a similar manner. But anyway, we will not go through that, the argument, because it is beyond the scope of our course here. Okay, so but I will just give you the result here. Okay, that result was obtained by a gentleman called Carson. So we are now looking at the result for a general modulating signal. General modulating signal. When I say general modulating signal, what do I mean? Like music signal or speech, like that. Because this result I cannot use it for my general signal, right? This result I argued based on the sinusoidal modulating signal. Now I would like to find the result for bandwidth in the case of general modulating signal. So what can you say about the bandwidth? See, I am only giving you the result. We are not giving or we are not going any discussion for that. To do that, let me define D, capital D, as the following ratio. It is peak frequency deviation divided by bandwidth of M of t, your message signal. Okay, peak frequency deviation we said del f. Let us say the bandwidth is capital W. Because M of t now is a general signal, it is not a sinusoidal signal. The only way you can characterize it is its bandwidth. Okay, so let me call D as the delta F by capital W, where delta F is the peak frequency deviation. Peak frequency deviation of FM signal or PM signal, delta F. And W is the bandwidth of the message signal. Then it can be shown that approximately the 98% bandwidth of the signal, that is the FM signal or the PM signal, is given by approximately 2 times D plus 1 times W. Very similar to the formula that we got here. Okay, there we said 2 times beta plus 1 times FM. Instead of FM we got W, instead of beta we got D. That's it. Okay, so and this is what this is a generalization of any arbitrary signals. Okay, so that's it. And this formula is given by a gentleman called Carson, and therefore this result is known as Carson's formula. Okay, for the bandwidth of an FM signal. Okay, so now again in this case, in this general case also, you can see that whether you will have a narrow band FM or wideband FM, you will really depend on the value of delta F. Okay, that is another way of looking at it. When beta is large, the delta F is large because beta is equal to del F by FM, and here D is delta F by W. If delta F is large, then beta is also large. So then it becomes wideband FM. So the point is, when delta F is large, the bandwidth will be governed largely by the peak frequency deviation, and that makes a lot of intuitive sense if you think about it. So what we are saying is the bandwidth will be essentially dictated by what is the highest instantaneous frequency in the modulated signal. Okay, that is Fc plus delta Fm. On the other hand, if delta F is small, this peak frequency deviation is small, which will essentially happen when beta is small. When beta is small, that means what? Narrow band FM. Okay, so I think more or less we discussed about the spectrum of our FM signal and also the bandwidth of the FM signal. So let me stop at this point. In the next lecture we will start with a topic called how do we get the modulation for this. Okay, I mean how do you generate the FM signal and how do we demodulate the FM signal and what are the methods are available. Okay, there are two methods basically, direct method and indirect method. So FM can be generated by using direct method and indirect method. That we will discuss in the next lecture. So let me stop. Thank you very much.